All right, so today we're going to review, finding our extrema, and then we're going to go ahead and find out how the second derivative can tell us some more things about the function. So go ahead and start the first problem. You should pause the video now. Make sure that you do the first problem out. I'm going to go ahead and do it, but pause and then check your answer. All right, so they asked us to find the intervals of increasing and decreasing and the local extreme and absolute extreme values. So I'm going to go ahead and I'm going to take the first derivative. I'm going to factor out this common factor of 12x. So x squared minus x, and minus 2. And keep factoring here, x minus 2, x plus 1. We're going to set that equal to 0. Because we have an x out front, that's going to give us an answer of 0. The negative 2 will give us an answer of 2, and then we'll have a negative 1. So these are all kind of interesting points to us. So because they ask about increasing and decreasing intervals, I'm going to need to use my first derivative. I'm going to put these values on my number line, negative 1, 0, and then 2. And then I'm going to plug in numbers around these values, right? So I'm going to plug in negative 2. I'm plugging it into the derivative. And I know that because I'm doing a first derivative test. So I'm going to plug in negative 2. And I'm going to plug it into the into this factored form. So I know the first term will be negative. If I plug in negative 2, the second term will be negative. And if I plug in negative 2, the third term will be negative. So 3 negatives will make a negative if I multiply those out. Then I'm going to plug in like negative a half. The first term will be negative. The second term, if I plug in negative a half, will be negative. And the third term, if I plug in negative a half, will actually be positive. So that's going to become a positive number. If I plug in 1, it's going to be a positive times a negative times a positive, which will make it negative. And if I plug in 3, it'll be a positive times a positive times a positive, which will make it all positive. So I can now answer my questions about increasing. It's increasing where the first derivative is positive, so that's from negative 1 to 0, and then again from 2 to infinity. It's decreasing where it is negative, where the first derivative is negative, so that's negative infinity to negative 1, and then again from 0 to 2. All right, and so how about some local extrema? Some local extrema here, because it changes from negative to positive at negative 1, there will be a local min at x equals negative 1, and it does that again at x equals 2, because it changes from negative to positive there. And there will be a local max at x equals 0, because it changes from positive to negative there. All right, to answer the questions about absolute extrema, I'm going to go ahead and put this thing in my calculator. So 3x to the 4th minus 4x cubed. When I say this thing, I'm talking about the function at this point. Minus 12x squared minus 9. And I'm going to use my table to type in these points of interest. So the points of interest that I'm looking at is I'm looking at negative 2. Because that's part of my interval, negative 2. I'm looking at negative 1 because that was a local min. I'm looking at 0. That was a local max. And then again, I'm looking at 2. 2 happens to be the end of my interval, but also a possible local min. So I'm going to type in all of those values into the function. So I'm going to type negative 2. I got back 23. If I type in negative 1, I got back negative 14, 0, I got negative 9, and 2 again, I got negative 41. So my absolute min is going to be at 2, negative 41, and my absolute max is going to be at negative 2, 23. Because I'm taking my highest and my lowest y values that I see, and those will become my absolute extrema. All right, so moving on from that, we can determine more about a function by looking at its second derivative, right? We already know that when we look at the first derivative, we know where the function has local extrema, we know where it can has absolute extrema on a given interval, and we know where it's increasing and decreasing. So we just did all that based on the first derivative. The second derivative tells us things about the function as well. Specifically, it deals with what we call concavity. And we saw this word in semester 1. We talked about how the function bends. So concavity is the shape of the function, and it can either fall into these two categories, concave up or concave down. So on the below here, here are some examples of something that is concave up, right? So concave up kind of bends like this or like this. And concave down, bends like this or like this. Generally, just to kind of keep these in our minds correctly, we usually say something like concave up, CCU is what we say, concave up, like a cup. It kind of goes really easily, that's a kind of easier thing to remember. And concave down, or CCD, like a frown. So this would be something that would be concave down. Now, it doesn't have to form the entire cup, as you see on the left-hand side. Just either side of the upward-facing graph would both be considered concave up, and concave down could be either side as well. Or it could be the whole thing, kind of depends. Now, the second derivative literally tells us where is this going to be concave up and where is this going to be concave down. And if it changes concavity, that's what we call a point of inflection, where the concavity is going to change. So that's what the second derivative is going to allow us to find out. So let's kind of do an example of this and see how this works. So first we're going to go ahead and find the second derivative. Now if you remember the second derivative, first we have to find the first derivative. So you say 3x squared minus, in this case, 26x plus 56. And then my second derivative, y double prime, I'm going to take that derivative a second time. So that's going to be 6x minus 26. We're going to find our critical points of the second derivative. So critical points, remember, are where the function is 0 or where it is undefined. And by that I mean the second derivative, where the second derivative is 0, undefined. So this is 6x minus 26. It's never undefined, but we can go ahead and set that equal to 0 in order to solve. So we get 6x equals 26. So x equals 26 over 6. Those are both divisible by 2, so I think this is like 13/3. And if you want to use your calculator to go ahead and get an approximation of that, you totally can, and you would get like about 4.3 repeating, something like that. So now we're going to go ahead and use sign analysis stuff, right? That's that number line. And we're going to use it with the second derivative, so I'm going to mark that f double prime over here to determine whether the second derivative is positive or negative. So we're going to take 4.3 repeating, so 4 thirds, 4 and a third, and I'm going to go ahead and using the second derivative, so using this equation, this 6x minus 26, I'm going to plug in a number less than 4.3. So I'm just going to go easy. I'm going to go ahead and plug in 0. If I plugged in 0, this would be negative. And if I plugged in a number like 6 times 6 would be 36, so that would be a positive number over here. Where the f double prime is negative, the graph is going to be concave down, and where f double prime is positive, the graph is going to be concave up. So we can go ahead and identify, just from what we've already done, that it's going to be concave up between 4.3 repeating and infinity. And it's going to be concave down between negative infinity and 4.3 repeating. And because our function changed concavity there, that means there's a point of inflection at, so I got 4.3 repeating, and then I'm going to go ahead and grab the y value for that. So 4.3, actually, I'm going to go ahead and type into my y equals, I'll type in this equation, x to the third minus 13x squared plus 56x minus 80. And just to make it easier, I'm going to go ahead and type in 13/3, so I get like a perfect answer. So I got like negative 0.074 as my y value for my 4.3 repeating. So there is a point of inflection on the graph. Now there doesn't have to be a point of inflection. It's all going to kind of depend on the function. Just to kind of give you an idea of just like a cubic function definitely changes concavity. We've seen graphs like this where this has, this would be a concave down concavity, and then this would be concave up concavity. And where they meet in the middle right here is what we call this point of inflection. So that's what we're talking about right here when we say that there's a point of inflection. All right, go ahead and give number 2 a try. You should pause the video and I will go ahead and do it myself. And then you're gonna practice a couple. I'm gonna talk to you really quickly about number 4 before we sign off. So go ahead, like I said, pause the video. Okay, so what I ended up getting here was that I had that it was concave up before 1/3, concave down after 1/3, concave down after 1/3, and then there was a point of inflection at 1/3, comma, negative 0.926. So just keep in mind, by the way, over here, when I label this graph, I'm not being just like annoying. I highly recommend I'm going to ask that you do that because later on in this exact same packet, we're going to need you to do the first derivative test to talk about increasing and decreasing, as well as extrema. And then also I'm going to add in the points of inflection. So if we don't label those number lines, then I can't ever use them to check what it is that you've been doing. So in a second, I'm going to ask you to go ahead and practice this. I just want to kind of talk really quickly about number 4. If I was to go ahead and take the derivative of number 4, sine of x, right? Hopefully you guys remember I would get cosine of x. And if I was able to take the second derivative, so take the derivative of cosine of x, I'm going to get negative sine of x. So we have an interval here because we want to know where is sine of x negative, where is it 0 in between negative pi and pi. So that's kind of important to know because sine of x will equal 0 many, 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 many times. And so when I put these numbers on my number line, right, I'm like, okay, well, where is sine 0? So, we're thinking over here about our unit circle. Sine is the y values. So where are the y values 0? Well, there's 0 here and here. It's just a regular sine function. So honestly, it's going to be 0 at negative pi and positive pi, right? So the endpoints of this graph are also the values where it hits the x-axis. And so therefore, where those critical points are the same as the endpoints in this case. So those are the values that we want to check, negative pi and pi. I know that we're only looking between negative pi and pi, but we're going to want to make sure that we look on either side of that as well in order to figure out whether or not we have points of inflection here. So this one's a little bit harder. This is a negative sine graph, so it will be going from the middle of your graph down, first of all. I don't know if this is kind of ringing a bell, but like we'll be kind of down here. would be our sine curve, so it'll come up over here. It kind of reverses the quadrants. This would be over here, this would be pi, and over here would be negative pi. And it's also equal to 0 at 0 as well. I forgot that one, sorry. Right, so this would be 0 and pi, and then also negative pi is over here as well. So we kind of need to know a lot about sine in order to figure this out. But between 0 and pi, you can see from this graph over here, we're going to be below the x-axis, so it's actually going to be negative. Between 0 and negative pi, we're going to be above the x-axis. After pi, so like something at like 3 pi over 2, for example, normally we'd be at -1, but because this is reversed, this will become positive. So we'd be like up here. And before negative pi, the same kind of deal goes into effect. Normally we'd be positive, but because it's negative, we're actually below the x-axis. So in this case, we are concave down between 0 and pi. We are concave up between negative pi and 0. And we have a point of inflection at 0, 0. Hopefully that makes sense to you.